In our discussion of the decibel operator, we made a point of saying that the decibel operator can only operate on a coefficient, a unitless value. The problem is, what is the log of time, or what is the log of distance or energy? What would the resulting units be? So we said it always had to operate on a coefficient, power gain, for example, of an amplifier, or the transmission coefficient of a filter, for example. But you may have heard statements where someone says, talk about power in terms of a decibel operator. The output power is 5 dBw, or the input power is 17 dBm. And of course, this would imply a decibel operator here. But of course, we're talking about power. Power, the rate of energy flow in joules per second. So how can we apply a decibel operator to a value like power, which is not unitless? And of course, the key thing here is it doesn't say 5 dB or 17 dB. It says 5 dBw or 17 dBm. So these are new operators, and they're similar to the decibel operator, but they aren't the same as the decibel operator. To express power with a log operator, we have to apply sort of a simple trick. Let's say we have some power that we'll represent by the variable P. This power could be any of the power that we've discussed: available power, delivered power, absorbed, reflected, incident, net. Regardless, what we could do is take that power and normalize it by dividing by 1 watt. The result, of course, now is a unitless value. If we take that power P in watts and divide by 1 watt, we get a number which is unitless. And so, for example, if our power were 2,500 milliwatts, we take that power and divide by 1 watt, which of course is 1,000 milliwatts, and we get a value of 2.5. Of course, it's not 2.5 watts. The watts units have canceled out here. This is a coefficient. And this is kind of a roundabout way of now stating the value of 2,500 milliwatts. What we're saying is the power P is 2.5 times larger than 1 watt. Well, 2.5 times larger than 1 watt, of course, would be 2.5 watts. But again, by stating it this way, 2.5 times larger than 1 watt, we can apply the decibel operator to this coefficient, this multiplier of 2.5. So we can take that coefficient, that normalized power, and then apply a log operator to it, the decibel operator to it. And when we do so, we define a new operator, which we call the dBw operator. The dBw operator operates on some power. But what it really is simply taking that power and first, in the operation, divided by 1 watt. Normalize it, making this ratio P divided by 1 watt into a coefficient, and then we can apply the decibel operator to that coefficient. And so, combining these two steps, we see the dBw operator is take the power divided by 1 watt, and then take 10 log 10 of that unitless result, the dBw operator. Let's say this power P then is a value that's greater than 1 watt. In that case, when we take that power and apply the dBw operator to it, we would find a value which is greater than 0. In other words, a value that's positive. A power greater than 1 watt, when expressed with the dBw operator, provides a value that is greater than 0, a value that's positive. Conversely, if we have a power that is less than 1 watt, then the ratio that we end up with is less than 1, and when we apply the decibel operator to it, we get a negative value. If the power that we are, again, trying to express is less than 1 watt, then we apply the decibel or the dBw operator to it, we get a value which is negative. And of course, from these two, we can conclude correctly that if the power is precisely equal to 1 watt, then the result when applied dBw is equal to 0. And of course, if the power is 1 watt, we normalize it by 1 watt, we get a value of 1. And 10 log 10 of 1 is equal to 0, which is why dBw, when applied to a power of 1 watt, gives us a value of 0. Greater than 1 watt, the dBw result is positive, less than 1 watt. The dBw operation result is negative. Power is exactly equal to 1 watt. The dBw result is 0. We can do some examples to show this. Let's say we have the power of 100 watts. So we take 100 watts and normalize it by dividing by 1 watt. Then, of course, we get a value of simply 100. 100 is 10 squared, and we can use our identity, log identity, and pull that 2 out front. And so we have 2 times 10 log 10. 10 log 10 is 10, and therefore we have 20 as the result. Or let's say we have a power of 1 milliwatt. Well, we take 1 milliwatt and we divide by 1 watt. Well, 1 watt is 1,000 milliwatts. We need to make sure that we have the same units on numerator and denominator so we can cancel them out. 1 divided by 1,000 is 10 to the minus 3. Again, we pull the minus 3 out front. 10 log 10 of 10 is equal to 10. We multiply that by minus 3, and our result, therefore, in the dBw operator is minus 30. Let's think about what this means in terms of a decimal operator. dBw is equal to 20. What we're really saying is our power is 20 dB larger, 20 dB bigger than 1 watt. 20 dB is 100, and therefore we're saying the power is 100 times 1 watt, or 100 watts. Here we go through and we get a value of minus 30 for our dBw operator. We're saying that our power is 30 dB less than 1 watt. 30 dB less. 30 dB is 1,000, and so we say that the power is 1/1000th of 1 watt. Of course, 1/1000th of 1 watt is 1 milliwatt. So think about what these results mean in terms of decibels. Again, if we get a value, let's say, of 23, all right, 23, we know the 20 gives us a factor of 100, the 3 gives us a factor of 2. That would be 200 times larger than 1 watt. All right, so now let's look at the other operator, dBm. What does this mean? dBm is very much related to dBw. The only difference is that we normalize with a different power value. Instead of taking the power P and divide it by 1 watt, we take the power P and we divide it by 1 milliwatt. And so this is the dBm operator. We go through and take the power and divide by 1 milliwatt and then apply the decimal operator. Again, 2 operations. Divide P by 1 milliwatt and then apply the decimal operator to that coefficient that results. And so this is our dBm operator, a way of expressing our some power P. In this case then, if the power P is greater than 1 milliwatt, the result for when applying the dBm operator would be a value that is greater than 0, in other words, a positive value. If the power is less than 1 milliwatt, our coefficient would be less than 1, and therefore applying the dBm, or the decimal operator, to that coefficient, rather, we get a value that is negative, a value less than 0. And from these two, then, if the power is precisely equal to 1 milliwatt, then the dB operator provides a value which is exactly equal to 0. So again, think about how this maps from power in milliwatts to the result when we apply the dBm operator. If the power is less than 1 milliwatt, the result is negative. If the power is greater than 1 milliwatt, the result is, if the power is greater than 1 milliwatt, the result is positive. If the power is less than 1 milliwatt, the result is negative. And if the power is equal to 1 milliwatt, the result gives us precisely a value of 0. A few examples then. Let's say we have a power of 100 watts and we want to express it with the dBm operator. Well, 100 watts is, of course, 100,000 milliwatts, 10 to the 5th milliwatts. So 10 to the 5th milliwatts divided by 1 milliwatt, the milliwatt cancels out and we get a value of 10 to the 5. Pull the 5 out front, 10 log 10 of 10, of course, is equal to 10. And so we multiply that by 5 and we get 50. The dBm operator, when applied to 100 watts, gives us a value of 50. And what that says is the power is 50 dB larger than 1 milliwatt. In other words, the power is 100,000 times larger than 1 milliwatt. And of course, 100,000 times larger than 1 milliwatt is 100 watts. Or if our power were 0.5 milliwatts, just 1/2 a milliwatt, we would go through and apply the dBm operator, divide by 1 milliwatt. The milliwatt cancels out. We get a value of 0.5, or 2 to the minus 1. We pull the minus 1 out front. 10 log 10 of 2 is equal to 3. Not exactly, but close enough that we'll call it 3. And therefore, minus 1 times 3 is minus 3. In other words, we're saying that the power in this case is 3 dB less than 1 milliwatt. 3 dB less means 1/2. 1/2 of 1 milliwatt is 0.5 milliwatts. Another important operator that's associated with dBm and dBw are their inverses. And so we're going to find an inverse operator. And in this case, if we have a value P that is expressed with a dBw or dBm operator, and we say what is the actual value in terms of watts or milliwatts, we can use these inverse operators to convert back to the original value of P. So in this notation, this dBw of P, that is the power expressed with the dBw operator. This is the power of P expressed with the dBm operator. Again, what we're trying to get back to is the original value P expressed in watts or milliwatts. And we can do the math. We can invert the dBm and dBw operator and show that the result is this. Look carefully at this. What we're doing is taking the result of the power in dBw and divide it by 10. And then we take that value to the 10th power. And then, and this is the most important part, we multiply that result by 1 watt. This term out front is a unitless value. And of course, our power has units of watts, joules per second. And so we take this unitless value and then we multiply it by 1 watt. And that gives us our power in terms of watts. The similar thing here, when we take the inverse operator, we take the power when expressed in dBm, divide by 10, take that to the 10th power, and then, or the 10 to that value, rather, and then we multiply that by 1 milliwatt. This is a unitless coefficient. Then we multiply it by 1 milliwatt to get a value of power in milliwatts. Now, this may seem superfluous, and students oftentimes leave this out or think I'm saying the result is in watts. No, this is actually what we take this value and multiply it by 1 milliwatt. Remember, when we define the value of dBm, we take the power and we divide by 1 milliwatt. That doesn't seem to be controversial. Students understand the necessity of dividing by 1 milliwatt. In the inverse, though, it should be no surprise that we also need to take a value and multiply that value by 1 milliwatt. And so don't forget to do this multiplication to get the units to turn out correct. So for example, let's say we have a value P1 and we express this value power P1 in terms of the dBm operator. Let's say we get a value of 6. And we say, all right, the power P1 when expressed with the dBm operator is 6. What is the value of P1 in milliwatts? Well, we can apply this directly into our inverse operator. We put 6 right here, so we get 6 divided by 10, 10 to the 6 divided by 10. That turns out to be 4. We multiply that by 1 milliwatt, and of course we get 4 milliwatts. Again, kind of a fancy way of saying our power. Our power is 4 times 1 milliwatt, and of course that means it's equal to 4 milliwatts. Which operator then do we use to express a given power? Just like we can express any power in terms of milliwatts or watts or kilowatts or microwatts, we can express that value with a decimal operator in terms of dBw or dBm or some other normalization factor. If we go through and we take a power, let's say, that's equal to 1 watt, and we express it with the dBw operator, of course, in that case, we get a value of 0. But if we express that same value of 1 watt in the dBm operator, of course, 1 watt is 1,000 milliwatts, and so we get dBm, we get 10 to the 3rd, and that gives us a value of 30. 30 dB larger than 1 milliwatt is a value of 1 watt. If we have a power equal to 1 milliwatt, then in that case, in dBw, we get a value of minus 30. 1 milliwatt is 30 dB less, 1/1000th of 1 watt, which is why we get minus 30. Of course, we can express that with the dBm operator, and we get a value exactly equal to 0. Let's say we take a power equal to 64 milliwatts. With the dBw operator, we get a value of minus 12. If we apply the dBm operator, we get a value of 18. Notice in each one of these cases, the value expressed with the dBm operator is precisely 30 larger than the value expressed with the dBw operator. 30 is 30 to 0, or 0 up to 30, minus 30 up to 0, minus 12 up to 18. This result, the fact that a power expressed in dBm is always a value of 30 larger than the same power expressed in dBw, is always true. And so we can say that the difference between the operator applied to some power P in dBm minus the same power applied to dBw is going to be 30, or written the other way, we could write it in this form. dBm is dBw plus the value of 30. And we can prove that, and showed that here. The dBm operator applied to a value P is by definition equal to this. And then we can go through and multiply by 1 being 1,000 milliwatts divided by 1 watt. And then rearrange things a bit here. And of course, the key thing is the log of x times y is the log of x plus the log of y. And so we get a value then that is here. And this is the identity that's shown here. So we always know if I want to convert, if I know the power in dBw and I want to express that in dBm, it's pretty simple. Take the value in dBw and add 30 to it. Conversely, if you know the value dBw and you want to dBm and want to express in dBw, then subtract 30. Everything we've done this far is a mathematical explanation of these operators, how they're defined, how we calculate them, and so forth. But when we talk about a power and use these operators, we have a problem in that we have to use the English language to express what we mean, or if we write about these values. And so there's a bit of a semantic problem that occurs when we use the decimal operators dBm or dBw, or a decimal operator in general. So for example, let's say we have a gain of some amplifier, and we apply the decimal operator, and we get a value of 16. How do we convey that in either written or spoken English? What we'd say is, we should say, if we apply the decimal operator to the gain G, the result is 16. Or we might say 16 is the value of the gain when expressed with the decimal operator. And I think for the most part, in my explanation thus far, I've used that kind of a statement in terms of when we apply the decimal operator. We apply the decimal operator to the gain value, and the result is 16. Now, the examples on the previous page are precise and unambiguous, but they are also a little bit verbose and ponderous. And so engineers typically shorten things. If we say that the gain of the amplifier when applied to this, when the decimal operator is applied to the gain of the amplifier, we get 16. Instead, the engineer says the gain of the amplifier is 16 dB. This causes problems, but it really causes problems when we apply the same sort of logic to the dBm and dBw operators. For example, let's say we have a power, let's say the absorbed power of our match load is equal to 8 milliwatts. If we apply the dBm operator to 8 milliwatts, we get a value which is 9. What we should say is the absorbed power, when expressed using the dBm operator, has a value of 9, or 9 is the value of the absorbed power when expressed with the dBm operator. Those would be complete, detailed, unambiguous statements. Instead, though, we use something more compact. We say, generally, as engineers, the absorbed power is 9 dBm. And that's where the problem comes in. Why is it so much of a problem to say the absorbed power is 9 dBm? The problem when engineers say things like the gain is 13 dB, or even more likely if we say the absorbed power is 9 dBm or the available power is minus 17 dBw, is that these decibel statements are interpreted as physical units. I have 9 joules, or I have 9 dBm. I have 9 kilometers or 9 dBm. They sound like units. And the key thing about these operators is they are not physical units. There are no such thing as dBs. And you can tell when there's a problem where an engineer will say something like, I have 13 dBs of gain, or I have 9 dBms of power. And in that case, you can tell that the engineer is interpreting dB or dBm as countable things, units that we can add or double. I started out with 4 dBms, and then I was able to locate 2 more dBms, and when I added 2 that I got 6 dBms, and finally I found another dBm in my coat pocket, and gosh, now I'm all the way up to 7. But then, of course, that's not the case. dBm, dBw, dB are mathematical operators, not physical units. I wouldn't say that the angle, some angle, theta is equal to 0.7 cosines. Now, I might say the cosine of that angle is equal to 0.7, but that does not mean it is 0.7 cosines. Get another 0.5 cosines, and I got 1.5 cosines in total. We wouldn't talk that way or speak that way, but that's the same thing as what we have for decibels. Decibel is an operator, just like cosine is an operator, or tangent is an operator. So if we have an absorbed power of 8 milliwatts and we want to express it with the dBm operator, we would find that value of 8 milliwatts turns out to be 9 when expressed with the dBm operator. So we would say that the absorbed power is 9 dBm. Again, that's a more compact way of expressing what we mean, but one that implies or introduces a lot of ambiguity, because when we say the absorbed power is 9 dBm, oftentimes engineers will interpret that as we have 9 dBms of power. And then again, frequently that's what you'll hear engineers say, 9 dBms of power. But again, dBms are not units. Perhaps the best way to illustrate this point is with an example. Let's say we have some power, we'll call it P1, and that power, when expressed with the decibel operator, is 6. We might say P1 is equal to 6 dBm. Consider a second power, P2. If we apply the dBm operator to P2, we get a value of 10. In other words, we might say P2 is equal to 10 dBm. The question then is, what is the total power? If we were to add these together, if we take the value of P1 and P2 and add it together and get PT, what is the total power when expressed in dBm? If we decide that dBms are units, the answer is pretty clear. If I have 6 dBms and I add to it 10 dBms, clearly I have 16 dBms. 6 plus 10 is 16. If I had 6 oranges and I added 10 oranges to them, I would have 16 total oranges. Why doesn't that work with dBms? Well, it doesn't work with dBms because dBms, again, are not a unit. They are not a countable object. It is an operator. So 6 dBms plus 10 dBms is not equal to 16 dBms. How do we solve this problem? Well, it's important, and anytime you have a concern or uncertainty involving the operation or the application of a decibel operator, you need to go back to the mathematical definition, and that definition has a log in it, 10 log 10. And so we need to know our identities associated with logarithms to successfully go through and figure out problems like this one. Now, log operators are very helpful when we are expressing values which are products or ratios. For example, log of x times y is the log of x plus the log of y. Or the log of x divided by y is the log of x minus the log of y. But what about if we're trying, as we are in this case, to apply the log of x plus y? What's the identity for the log of x plus y? What does it simplify to? Well, there is no simplification. The log of x plus y is the log of x plus y. Certainly it's not equal to the log of x plus the log of y. That would be equal to the log of x times y. And that's the problem we run into, again, with the earlier problem. We can't go through and find the sum of two powers by using the log of each of those two powers. So if we wish to find the value of P1 plus P2 when expressed with the dBm operator, we have to go through and first explicitly determine the power of P1 and P2 in watts or in milliwatts. And so we take this result, P1 is equal to 6 dBm, and we apply the inverse operator. If P1 is 6 dBm, how much is that in watts? And we apply the inverse operator and we get 4 milliwatts. And it makes sense. 4 is 4 times larger than 1 milliwatt. 4 is 2 squared. 2 squared, 2 to the second power. We take that second power multiplied by 3, and that gives us a decibel of 6. Remember, the decibel operator on value of 2 gives us 3. 2 to the n gives us a value of n times 3. Likewise, for P2, the power P2, expressed with the dBm operator is equal to 10. What is the value of P2? Well, we apply the inverse operator. Again, make sure we multiply by 1 milliwatt here. 10 times 1 milliwatt. It's 10 times larger than 1 milliwatt. In other words, it's 10 milliwatts. So now we know P1 is equal to 4 and P2 is equal to 10. So if P1 is 4 and P2 is 10, the sum of those two powers gives us a value of 14 milliwatts. That's the total power. What is that total power when expressed with the dBm operator? Well, we insert it into the dB operator, 14 divided by 1. Take 10 log 10 of 14 and we get 11.46. And so it turns out here that if P1 is 6 dBm and P2 is 10 dBm, then the sum of P1 plus P2 is equal to 11.46 dBm. And so this is a very important thing to keep in mind when you do these operations. When we're adding or subtracting power, we need to almost certainly take our inverse operator and convert back into milliwatts or watts before we do the subtraction or addition. And then if we want to express it with the log decibel operator, then do the operator after we've done that addition and subtraction. A famous question that often arises in, let's say, technical interviews for a job for electrical engineers. If you say you know something about, microwave engineering and such, they might say, what is the sum of 0 dBm and 0 dBm? If P1 is equal to 0 dBm and P2 is equal to 0 dBm, and we add P1 and P2 together, what is that total result when expressed in dBm? Well, 0 dBm plus 0 dBm turns out to be 3 dBm. Think about that. Frequently, students will mess up decibel operators, particularly if power or gain is expressed with a decibel operator, and then we ask for a result. Likewise, with respect to the decibel operator, there's a tendency to try to manipulate the decibel operators directly, to add them or subtract them or do something to get the result. And the question is, can you do that mathematically? Is it mathematically proper, valid to apply those operations? And many times students aren't sure. They just sort of guess that perhaps maybe this will give them the right answer. But the decibel operators that we use here are not some highfalutin mathematical expressions. They're actually very simple. 10 log of 10. Multiplying by 10 is not hard. Taking the log of an operator, of a value rather, with respect to 10 is maybe a little bit more abstract that you're used to, but again, logs are things that you probably learned about in middle school, so we should be able to go through and work our way through it. The key thing is don't apply any mathematical manipulation until you're sure that the answer is going to be valid. And to do that, you need to make sure you understand your log identities. And so this is kind of a list of things that you want to keep in mind anytime we use decibel operators. The log of x times y is equal to the log of x plus the log of y. The ratio of x and y is equal to log of x minus the log of y. 1 over x, therefore, is equal to minus log of x. X to the y power, we pull the y out front, we get y times log of x. This is a very useful one in electrical engineering. Finally, the value of the log of x plus y is simply the log of x plus y. We can't simplify it further. Neither can we take the log of x minus y and simplify that further. If we want to find the log of x plus y, we need to explicitly determine the value of x and the value of y before we add them, and then and only then do we apply the log operator.